Welcome grade 12s to this physical science lesson. My name is Gillian. What we're going to do today is consolidating work energy power. Now this is a pretty tricky section. So we're going to have a look at two questions that come from an exam paper, and we're going to tease it out, we're going to break it down, and we're going to look at the real detail and what we need to think about when we're answering these questions. So let's head on to the first one. So the first one comes from last year. And it's about a roller coaster. So you can see this diagram, they've given you a diagram. A roller coaster are a car of mass 200 kilograms with the engine switched off. Okay, so that's interesting information. Travels along a track A, B, C. So if we look at the picture, we can see there's A, there's B, and C is right at the top, which is a rough surface. So now this word, rough surface, is an indication that they're telling you about friction. So if there is a rough surface, then friction invariably is going to pop up in a later question. As shown in the diagram, at point A, which is 10 meters, there's 10 meters above the ground, the speed of the car is 4 meters per second. Okay, so that's velocity. There we go. So that would be the initial velocity. I'm just going to write there VI. Okay, at point B, which is at a height of h, okay, so we don't know that height. So my brain is thinking, well, they're probably going to ask me to calculate that height at some stage. The speed of the car is 2 meters per second. All right, so that is going to be a final velocity at 2 meters per second. During the motion from point A to point B, 3,4 times 10 to the 3 joules of energy was used to overcome friction. Okay, so that's quite important value. Let's keep that in the back of our minds. We need to ignore rotational effects due to the wheels. Okay, so that's just to tell you, we're not making this a really complicated problem. We could take into account the friction of the wheels, but that is for university level. So we're just dealing with the friction on the track. Right, so what is the first question that they're asking? Define the term non-conservative force. All right, so our understanding of a non-conservative force is a force that takes energy out of a system, and that force is friction. So friction is the non-conservative force that would take energy out of a system. Non-conservative, it's not conserving the energy of the isolated system. How would we put this into a definition? So the definition that we know is that with a non-conservative force, it is a force that does work in moving an object from point A to point B, and that the path is dependent. The work is dependent on that path that is taken. In a conservative force, the path is, the work is not dependent on the path. So the word that you would have to write down is that the work is dependent on the path taken. And that makes sense because if friction is a non-conservative force, it would depend on how long that object is moving on that surface for the energy to be removed from the system. So if you are a cyclist and you fall off your bike onto the tar, it would depend, the wound that you would get would depend on how far you slide on that surface. The further you slide, the more serious the burn, the friction burn is going to be, the welt is going to be on your body. Right, let's look at B. Calculate the change in kinetic energy. Calculate the change. So we're talking about delta, change of the car after it has traveled from point A to point B. Right, so change in kinetic energy. They tell us which energy they want us to work with. Kinetic energy. So what is the definition, what is the formula for kinetic energy? Well, it is a half mv squared. So what is the change then? Well, it would be from the final velocity to the, that would be the final velocities over here. Let me just rub that out so we don't confuse ourselves. It's not final velocity there. It's going to be initial velocity. So that's the initial velocity to final velocity. So we would need to find the difference between those two energies. So a half mv squared, and that's the initial. So let's pop this into the formula and calculate it. So a half and mass is the same, so we can remove that. And then we end up with final velocity squared minus the initial velocity squared. Don't forget those squares. Important to pop those in. So that's where the attention to detail comes into answering these questions. Okay, so a half times the mass. We've been told that the mass of this car is 200 kilograms. What is the final velocity? The final velocity is here. It's telling you that this car is actually slowing down, right? Obviously from the effect of friction. So that's going to be 2, and we're going to square it. The initial velocity is 4, and we're going to square it. And so we end up with an interesting answer here, because this is going to be, I want to change color so we can have a look at the thinking. So this is going to be 4, right? That is going to be 16. So we've got 4 minus 16. How's that? So that's going to end up in a negative value. So my answer, my final answer, once I've used my calculator, is going to be minus 1,200 joules. Does that minus confuse you? Is it true? Is this answer true? Well, let's think about this. If friction is removing energy from a system, then the change in the kinetic energy is going to be negative. So absolutely, this is a good answer. Right, let's look at the next question. Use energy principles to calculate H. There we go, we need to calculate H. So what energy principles do we have? Well, we know that this system is one of non-conservative force. They've already asked us to give the definition of a non-conservative force. So the work done would be of that of a non-conservative force. We know this equation to be the change in the kinetic energy plus the change in the potential energy. Now that's the clue, the change in potential energy, because we know that potential energy is mgh, the mass of the object times gravitational acceleration times the height. And we want to find height. That's the question. Find h. Okay, so what about all this information? Do we have it all? So I'm going to write on the side over here everything that we know so far. I'm going to flip back to our initial question, and let's have a look. So we've been told that the work or the energy used to overcome friction is 3,4 times 10 to the 3 joules. So let's move on now to write in our information. So if the energy used or transferred is equal to that, then that's the work done, right? So we then have the work done by the non-conservative force, that's friction, is 3,4 times 10 to the 3 joules. Okay, so we've been told that. What have we worked out? In the previous question, we've already worked out that the delta, the change in potential energy, kinetic energy, is, let's go back to our answer just to check it, was 1,200 joules. So we know that, 1,200 joules. Okay, let's work now with this equation that we know about. So W, work done of a non-conservative force, equals the change in kinetic energy plus the change in potential energy. So how are we going to write it? We're going to write it as mgh final minus mgh initial. Again, we can remove that, which is common, and so we have mg final height minus initial height. All right, let's substitute in. The work done by the non-conservative force is being given to us. Here it is here. We need to write that as a negative value. The reason why is because that is the work done to take energy out of the system. It is because of friction, and so we're going to write it as a negative value, 3,4 times 10 to the 3. Our change in kinetic energy, because it is also referring to the energy that is removed from the system, is also going to be a negative value. That's what we got. We got the negative value, so we're going to substitute that in, 1,200. Plus, right, we know our mass. Our mass is 200 kilograms. We know what the gravitational acceleration is. It is 9,8. What about our height? Well, which height are we wanting to find? We're wanting to find the height, oops, let's take that away. We're wanting to find the height at the end of this run, so at B. So that is the final height. What is the initial height? So the initial height when the car is released is 10 meters. So we're going to add that in there. We are going to rearrange this equation so that we make h the subject of the formula. I'm going to change color so that we can see nicely. So there we go. We've made it the subject of the formula, and this is what it's going to look like. 3,4 times 10 to the 3 plus 1,200. Okay, so this effectively gets moved to that side. That's why we're plussing it. We're then going to divide by 200 times 9.8. So you can see over here, we want to, because it's times by the height, we want to then divide by it on each side. And then we have to remove the minus 10, and that becomes plus 10. Once we pop that into our calculator, we end up with an answer of 8,88 meters. Right, so that's quite a lot of calculating. There are little tweaks in it, so you need to remember to put in the negative that belongs to the delta kinetic energy, the change in kinetic energy. You also need to place the negative referring to the fact that work is done taking energy out of the system. So it needs to be a negative due to frictional force. Right, grade 12s. We are going to take a quick break. When you come back, we have another question. Welcome back, grade 12s from the break. Right, we're heading straight into the next one. Let's read it. In the diagram below, a 4 kilogram block is lying on a rough surface. That's telling us we've got a frictional force. Horizontal, so it's on a rough horizontal surface. It's connected to a 6 kilogram block with a light inextensible string. That's a big word. All it means is that the string can't act like a spring and get bigger. So it really has no impact on the whole system. And it's passing over a light frictionless pulley. Okay, so friction on this pulley is going to be ignored. Initially, the blocks are held at rest. That's important information. It means that the initial speed of this 4 kilogram block is 0, and the initial speed or velocity of the 6 kilogram block is 0. Right, let's look at the first question. State the work energy theorem in words. Okay, so we know that the work energy theorem is about the net work. And so the net work done on an object is equal to the change in the kinetic energy of that object. Those are important words. You can write them down. We don't have time right now to do that. Let's get to the next question. It now tells us that the blocks are released. So from stationary, they were stationary now, they were at rest. It has now been released, and this whole system has dropped. It falls through a distance of 1.6 meters. Draw a labeled free body diagram. Free body diagram, that's the one with the dot for the 6 kilogram block. Okay, so here's the dot. It represents 6 kilograms. The 6 kilogram object. What forces are working on it? Well, we definitely have got the gravitational force, like that. So Fg, we're going to label it. And what else? Well, there's tension in this string, keeping the 6 kilogram and the 4 kilogram block joined together. It is not as big. This force of tension is not as big. If it were, then there would be no movement, right? But because the 6 kilogram block is moving, and it's moving with the force under the influence of the force of gravity, the force of gravity arrow has to be bigger. So here we have the tension force. So there's the force of tension. You can write there if you want to, force of tension. So be precise about this. Make sure that this arrow representing tension is smaller than the arrow representing the gravitational force. Our next question, calculate the work done by the gravitational force on this 6 kilogram block. Right, so we know that we have this equation. So the net work done, because they're asking us about that, is the net force times by the distance moved cos of theta. What are we being asked to find? We're being asked to find the work done by gravity. Okay, so the gravitational force. And so what will this then change to? It will change to the force of gravity times by the distance cos of theta. Right, let's rewrite this. How do we find this force? Well, we know it's mass times the gravitational acceleration. What is the distance covered? Well, or displacement, they've told us that it is 1.6 cos theta. What about theta now? Now, the movement is in this direction. The gravitational acceleration, the force of gravity, is in this direction. There is no change in there's no difference in the direction of motion or the direction of displacement and the force that has been applied. So for cos theta, we are going to write cos of 0 degrees. There's no difference. Let's add in the values. The mass is the 6 kilogram block. That's what they've asked us. Gravitational acceleration is 9.8. Our distance, displacement is 1.6, and cos of theta. Cos of theta is going to be 0 degrees, and cos of 0 degrees is always positive 1. We calculate this, and our answer is going to be 94.08 joules. Excellent. That's a lovely question. Next question is a little bit more complicated, and one which we have to be quite thoughtful about. So the coefficient of friction, and it's not just any friction, it's kinetic friction. The coefficient of kinetic friction between the 4 kilogram block and the horizontal surface is 0.4. Okay, so we've been introduced to friction. We've been told to ignore the effects of air friction. Now use energy principles to calculate the speed, the V, of the 6 kilogram block when it falls through this distance. So we're being asked to find the final velocity because it's already fallen through the 1.6 meters. It is still attached to the 4 kilogram block. So this is a whole system because it's connected. The 4 kilogram and the 6 kilogram are connected together. It is a system that we need to work with as a whole. But we're first going to look at the net work done in this whole system. From our definition, we know that the net work is equal to the change in the kinetic energy of the system. Okay, kinetic energy, we know, is a half mv squared, and we want to change, it's the change in the kinetic energy, so it would be minus a half mv squared. This would be the final, this would be the initial kinetic energy, velocity. So we've been asked to find that, the final velocity of this system, because they're connected, even though it says the 6 kilogram block. We have to calculate W net first. So let's think about all the forces that are acting on this 4 kilogram block. We have got a normal force. We have got a frictional force. There they tell us about it is the kinetic frictional force. Okay. I think that's about, we also have got this force, which is the gravitational force, okay, which is acting in that direction. Okay, so W net, let's work it out. W net is going to be the work of friction plus the work of the gravitational force plus the work of the normal force. What about our frictional force? So our frictional force, the work done by our frictional force, first of all, so that formula would be work is equal to the frictional force times the distance moved cos of theta, okay, cos of theta, plus this work done by gravitational force, which we've already calculated. I'm going to write that in there. What about the work done by the normal force? Well, movement of this whole system is in this direction. Normal force is up. So we're not going to use the normal force. It is going to be equal to 0 because it has no bearing on the direction of displacement. So we're going to put that in there as 0. What about this frictional force? We've been told that it's a kinetic friction. And we've been told that the kinetic friction coefficient is 0.4. So this is a key. We then need to work out using the formula that we've been given previously, which is coefficient of K times the normal force. Our displacement, delta x, is going to be the same as 1.6, because as the 6 kilogram block moves through that distance, so the 4 kilogram block moves exactly the same distance at the top, because they're connected. So that's going to be 1.6. What about cos theta? Well, cos theta, what about the theta? The frictional force is moving in the opposite, or working in the opposite direction to the motion, and so it has to be 180 degrees, plus the amount that we've already worked out. Okay. This is 0.4. It's been given to us, 0.4. Our normal force. Well, if we look at this block, we know that the 4 kilogram has got a gravitational force that is equal to 4 times 9.8. The normal force is exactly the same in magnitude but opposite in direction. So the normal force is going to be the same value in magnitude, 4 times 9.8 times the displacement cos of 180 degrees, and that 180 degrees tells us what the direction of the force is going to be. It gives us the negative value. We don't have to put in the negative value. So we end up now, running out of screen space, we end up, if we work all that out, we end up with a net value of work done, which is equal to 68,992 joules. Right, we are not finished. It might seem as though we're done, but we're not. Now we need to work with our change in kinetic energy. And so we are going to do that. However, with this one, because we've got 2 blocks that are involved here that are moving, we have to talk about the change in kinetic energy of both blocks. So the first one, a half mv squared, let me just write out the formula first, a half mv squared, so that's going to be the change, minus a half mv squared, so that is final, that's initial, that's of the block 4, so the 4 kilogram block, plus, I'm running out of space, I'll write it here, mv squared final minus a half mv squared of initial, that is for the 6 kilogram block. For our V initial, both of them are at rest, so it's equal to 0. So this whole term here is going to be 0. It falls away, 0, because our initial velocity is 0. And so we end up with a half mv squared final, and that is for the 4 kilogram block, plus a half mv squared final for the 6 kilogram block. If we substitute in our values, which I'm going to do, we have a half, the mass is 4 v squared of the final, plus a half 6 v squared final. We end up with this. Have a look at this. The final velocity equals 68,992 divided by 5. Now we have got to square root that. You see that square? We have to square root it, and so we end up with a value of 3,715 meters per second. This final velocity of the 4 kilogram block and the final velocity of the 6 kilogram block have to be the same because they are joined by the string. they're joined by the string, it means that both of them have to move at the same velocity. And that's why we end up with a v squared final, and we can work out then the velocity of the 6 kilogram block because both of them are moving at the same velocity. Right, grade 12s. I hope that has helped you with unpacking this kind of question, it's quite a complicated question. So I hope that's helped you with teasing out all the information and being able to work out the answers correctly. Grade 12s, good luck for your exams. See you later.